Every time the James Webb Space Telescope points at the ancient universe, it finds them. Tiny red specks that should not be there. Hundreds of them, glowing from an era when the cosmos was barely 600 million years old. Scientists call them little red dots, and they are not galaxies as we know them. They are not stars as we understand them. The leading explanation is that they are young black holes wrapped in cocoons of superheated gas, devouring matter at ferocious rates in an epoch when nothing that powerful should have existed yet. 341 have been catalogued so far. They appear in every deep image Webb takes, and they are forcing scientists to confront a possibility many hope to avoid. The early universe grew up too fast. If you enjoy journeys into the deepest mysteries the universe is hiding from us, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep bringing you stories like this one. Now, settle in and get yourself comfortable. Let's begin. There is a story scientists told themselves for decades. It was elegant, it was comforting, it made mathematical sense, and it went something like this. In the beginning, there was nothing recognizable. No stars, no galaxies, no planets, no light. The universe after the Big Bang was a scalding ocean of energy so hot that atoms could not hold themselves together. Protons and electrons tumbled through a blinding fog of radiation, colliding, separating, colliding again. Unable to form stable structures because the temperature was simply too extreme. For 380,000 years, this cosmic furnace raged. The entire observable universe, everything that would one day become 2 trillion galaxies and all the stars within them, existed as a seething plasma, smaller and denser than anything your intuition can process. Then the universe cooled just enough. Electrons finally latched onto protons. Hydrogen atoms formed for the first time. The fog lifted. Light was released in every direction, and that ancient glow still fills the sky today as the cosmic microwave background radiation. Scientists have photographed it with satellites. It is real. It is measurable, and it tells us exactly what the universe looked like at that infant moment. What it looked like was almost perfectly smooth. The cosmic microwave background shows a universe with temperature differences of only a few hundred, thousandths of a degree from one region to another. Those differences correspond to tiny variations in the density of matter. Some patches had slightly more material than average, others had slightly less. But the key word is slightly. The early universe was extraordinarily uniform, almost featureless, almost blank. And this is where the comfortable story begins. Because those minuscule density differences were the seeds of everything. Gravity, patient and relentless, would spend the next several 100 million years slowly pulling matter toward the slightly denser regions. Gas would accumulate, clouds would form, pressure would build, and eventually, somewhere in the darkness, the first star would ignite, but not quickly. Nothing happened quickly in this version of cosmic history. The universe needed time. After the cosmic microwave background was released, the cosmos entered a period that astronomers call the Dark Ages. No stars existed yet. No sources of visible light shone anywhere in the observable universe. Space was filled with neutral hydrogen gas, invisible and cold, drifting through an expanding void that grew emptier and darker with every passing million years. If you could somehow transport yourself to this epoch and open your eyes, you would see nothing. Absolute blackness in every direction. No constellations, no nebulae, no Milky Way. Just an infinite dark ocean of hydrogen stretching beyond comprehension. This darkness lasted for roughly 100 to 200 million years. In human terms, that sounds like an eternity. In cosmic terms, it was the universe holding its breath. Gravity was working during this silence, pulling gas into denser and denser knots. But the process was agonizingly slow. Dark matter, the invisible scaffolding that makes up roughly 85% of all matter in the universe, played the leading role. Because dark matter does not interact with light and does not experience radiation pressure, it could begin collapsing into structures earlier than normal matter. Dark matter halos formed first. These invisible gravitational wells then attracted ordinary hydrogen gas, funneling it inward, compressing it, heating it through gravitational contraction until finally, somewhere in the cosmos, a cloud of hydrogen reached the temperature and pressure necessary for nuclear fusion. The first star ignited, then another, then clusters of them. These were not stars like our Sun. Theoretical models predict that the first generation of stars, called population 3 stars, were enormous. Some may have contained hundreds of solar masses. They burned incredibly hot, incredibly bright, and incredibly fast, exhausting their nuclear fuel in just a few million years before dying in catastrophic explosions. These first supernovae scattered heavy elements into the surrounding gas, seeding future generations of stars with the carbon, oxygen, and iron necessary for rocky planets, and eventually for life. This period, when the first sources of light gradually switched on across the cosmos, is called cosmic dawn, and the standard picture of cosmic dawn was one of modesty. The first stars were impressive by individual stellar standards, but the structures they inhabited were small. The first proto-galaxies were thought to be tiny, irregular clumps of gas and young stars, nothing like the grand spirals and massive ellipticals we see in the modern universe. They were galactic embryos, barely luminous, scattered sparsely through an ocean of neutral hydrogen that still filled most of space. These small proto-galaxies were supposed to grow gradually. Over hundreds of millions of years they would merge with one another, accumulating mass through collision after collision. Small structures combined into medium structures combined into larger ones. This hierarchical process, called bottom-up assembly, was the backbone of the standard cosmological model known as lambda cold dark matter. The model predicted that the universe built its grandest structures last. Giant galaxies, massive black holes, rich galaxy clusters, these were all supposed to be late arrivals, products of billions of years of patient gravitational assembly. The early universe was supposed to be simple, dim, and immature, and for a long time the evidence supported this picture beautifully. The Hubble Space Telescope, which dominated deep universe astronomy for 3 decades, observed distant galaxies and confirmed that they generally appeared smaller and less organized than nearby modern galaxies. The farther Hubble looked back in time, the more primitive the galaxies appeared. This fit the model perfectly. The early universe was young and underdeveloped, just as predicted. Observations of the cosmic microwave background by satellites like COBE, WMAP, and Planck confirmed that the initial density fluctuations were small enough to match the gradual assembly timeline. Computer simulations running the lambda cold dark matter model forward from these initial conditions reproduced the large-scale structure of the modern universe with remarkable accuracy. Filaments of galaxies, clusters at the intersections, vast cosmic voids in between. The model worked. It was one of the great triumphs of modern physics. But there was one piece of this comfortable story that carried a particularly strong sense of reassurance, and that was the expected behavior of black holes. Black holes are the most extreme objects in the known universe. They are regions where gravity has overwhelmed every other force in nature, crushing matter into a point of infinite density, surrounded by an event horizon from which nothing, not even light, can escape. Stellar mass black holes form when massive stars exhaust their nuclear fuel and collapse. These objects typically contain between 5 and 50 times the mass of our Sun. They are violent, dramatic, and real. We have detected their gravitational waves. We have photographed the shadow of a supermassive black hole at the center of galaxy M87. Black holes are confirmed features of our universe. But the black holes that sit at the centers of galaxies are in a completely different category. These supermassive black holes contain millions to billions of solar masses. The one at the center of the Milky Way, called Sagittarius A star, weighs roughly 4 million times as much as our Sun. The black hole at the center of the galaxy Messier 87 weighs 6.5 billion solar masses. These objects are engines of extraordinary power. When matter falls toward them, it forms a swirling accretion disk that heats to millions of degrees and radiates energy across the electromagnetic spectrum. The most luminous of these feeding black holes, called quasars, can outshine their entire host galaxies by factors of hundreds. The Comfortable story said these monsters took a very long time to build, and the reason for this confidence came down to a single, well-understood piece of physics called the Eddington limit. When a black hole accretes matter, the infalling gas heats up and radiates intensely. That radiation pushes outward against the incoming gas. If the black hole tries to eat too quickly, the radiation pressure becomes so strong that it actually blows the food supply away, shutting down the accretion process. This creates a natural speed limit on how fast a black hole can grow. The Eddington limit is not a guess. It is a direct consequence of the balance between gravitational attraction and radiation pressure, and it has been confirmed observationally in many astrophysical contexts. Under Eddington-limited accretion, a stellar mass black hole born from the death of a first-generation star would need roughly 1 billion years of continuous feeding to reach supermassive scales. 1 billion years. That timeline meant that truly massive black holes should not appear until the universe was at least 1 to 2 billion years old, and even then only in exceptional circumstances where a black hole managed to accrete almost continuously without interruption. The standard expectation was that the largest supermassive black holes assembled their mass gradually, through a combination of steady gas accretion and mergers between smaller black holes over cosmic time. This was clean, this was logical, and it seemed to match the evidence available before Webb. But even in the Comfortable era, there were whispers of trouble, and those whispers had names. The first serious tremor came from ground-based surveys scanning the distant universe for quasars. Throughout the 2000s and into the 2010s, teams using instruments like the United Kingdom Infrared Telescope, the Panoramic Survey Telescope and Rapid Response System, and the Very Large Telescope in Chile pushed the quasar detection frontier to ever higher redshifts. Each new record-breaking quasar raised the same uncomfortable question: how did a black hole get that massive that quickly? One of the most famous examples is ULAS J1342 plus 0928, a quasar discovered in 2017 at a redshift of 7.54, corresponding to a time when the universe was only 690 million years old. The black hole powering this quasar was estimated at roughly 800 million solar masses. That is 800 million times the mass of our Sun, compressed into a region smaller than our solar system, shining with a luminosity that dwarfed the entire galaxy surrounding it. Getting a black hole that massive that early was theoretically possible under Eddington-limited growth, but only barely. It required the black hole to begin as a relatively heavy seed, not a typical stellar remnant of 10 or 20 solar masses, but something substantially larger, perhaps 1,000 solar masses or more. And it required that seed to accrete gas almost non-stop from the moment of its formation, never pausing, never being disrupted by mergers or environmental changes, feeding at or near the maximum theoretical rate for hundreds of millions of years without interruption. The margins were razor thin. One significant pause in accretion, one major merger that disrupted the gas supply, and the black hole could not reach its observed mass in time. Theorists responded with ingenuity. They proposed that the first black hole seeds might have been heavier than standard stellar remnants. Perhaps some primordial gas clouds collapsed directly into black holes without forming stars first, creating seeds of 10,000 solar masses or more. Perhaps the first massive stars formed in unusual binary systems, where collisions and mergers between stars produced exceptionally heavy remnants. Perhaps some black holes experienced brief episodes of super Eddington accretion, temporarily exceeding the theoretical speed limit by feeding through geometrically thick accretion flows that trapped their own radiation. Each of these proposals was physically plausible. None was observationally confirmed. They existed as theoretical escape hatches, ways to preserve the standard model by invoking mechanisms that were possible but unproven. Then there was GNZ 11. This object, initially discovered by Hubble in 2016 and later studied intensively by Webb, is one of the most distant confirmed galaxies ever observed. It existed when the universe was only about 400 million years old. That alone made it remarkable, but what made it genuinely troubling was what Webb's spectra revealed when the telescope turned its instruments toward this ancient source in 2023 and 2024. The data showed signatures consistent with an actively accreting black hole at its center, including high ionization emission lines that require an intense radiation field to produce. The implied black hole mass was estimated at roughly 1.5 million solar masses. Not as dramatic as the billion solar mass quasars, but in some ways more disturbing, because GNZ 11 existed at a time when the universe was so young that even modest black holes were difficult to explain. GNZ 11 was not supposed to look that mature. It was supposed to be a primitive, barely luminous smudge. Instead, it showed evidence of significant chemical enrichment, with nitrogen abundances far exceeding what simple models of early star formation predicted. The nitrogen overabundance suggested that multiple generations of stars had already lived and died within this system, recycling processed material back into the interstellar medium. Stars had to have been forming within GNZ 11 for at least 100 million years before the moment Webb observed it, pushing the onset of star formation in this object back to a time when the universe was only 300 million years old. At that epoch, most models predicted that star formation was just barely beginning in the most extreme environments. Scientists noted these objects. They published papers about them. They presented findings at conferences. They adjusted models slightly to accommodate them. But critically, these early quasars and bright galaxies could still be dismissed as rare statistical outliers. In a universe containing billions of galaxies, you expect a few to form unusually early through fortunate circumstances. A particularly massive dark matter halo collapsing in just the right way. A black hole seed that happened to find an uninterrupted supply of gas. A galaxy that happened to begin forming stars a few tens of millions of years earlier than its neighbors. These explanations were not comfortable, but they were tolerable. The standard model could stretch just enough to include a handful of precocious objects without breaking. The key word was handful. A few unusual quasars did not overturn a cosmological framework supported by decades of evidence. They were footnotes, not revolutions. The overall picture remained intact. The early universe was supposed to be simple. Black holes were supposed to grow slowly. Massive structures were supposed to take time. And if a handful of objects seemed a little too bright or a little too massive for their age, well, outliers exist. That is what many scientists told themselves. The model had survived challenges before. It would survive these too. And then Webb opened its eyes. The James Webb Space Telescope was not built to destroy the comfortable story. It was built to complete it. Decades of planning, engineering, and international cooperation produced the most powerful infrared observatory ever launched into space. Webb's primary mirror spans 6.5 meters across, constructed from 18 hexagonal gold-coated beryllium segments that unfold in space like a technological origami. Its sunshield, roughly the size of a tennis court, blocks heat and light from the sun, earth, and moon, cooling the telescope's instruments to temperatures below -230 degrees Celsius. This extreme cold is essential because Webb observes in infrared wavelengths, and any warmth from the telescope itself would blind its detectors. Infrared capability is the key to everything Webb does. Light from the most distant objects in the universe has been stretched by cosmic expansion. Ultraviolet and visible light emitted by early stars and galaxies has been redshifted into infrared wavelengths by the time it reaches us. Hubble could see some of this stretched light, but its infrared sensitivity was limited. Webb was designed to see far deeper into the infrared than any previous space telescope, giving it the ability to detect objects from the first few 100 million years of cosmic history. Objects that Hubble could only glimpse as faint smudges if it could detect them at all. Webb launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. It traveled to the second Lagrange point, a gravitationally stable location roughly 1.5 million kilometers from Earth, where it orbits the Sun in lockstep with our planet. After months of careful unfolding, alignment, and calibration, Webb began scientific operations in the summer of 2022. The first full-color images were released on July 12th of that year, and they were breathtaking. Deep field images showed thousands of galaxies crowded into tiny patches of sky. Their light stretched across billions of years of cosmic history. Nebulae glowed with intricate detail, invisible to previous instruments. Exoplanet atmospheres revealed chemical fingerprints that Hubble could never have detected. But the scientific community was not just admiring pretty pictures. Researchers immediately began analyzing the data for signs of the earliest cosmic structures. They pointed Webb at fields that Hubble had already studied, expecting to see the same faint, primitive objects with slightly better resolution and sensitivity. What they found instead was something that nobody had planned for. Almost immediately, Webb began detecting galaxies at extreme redshifts that appeared far too bright and far too massive for their age. Objects that existed within the first 500 million years after the Big Bang looked more developed than the standard model said they should. Some appeared to contain stellar populations that were already old, meaning the stars within them must have formed even earlier, pushing star formation back to absurdly early epochs. Others showed chemical enrichment levels suggesting multiple generations of stars had already lived and died, recycling heavy elements into the interstellar medium faster than models predicted. These early bright galaxies generated headlines and intense scientific debate throughout 2022 and 2023. Some researchers argued that the mass estimates were being inflated by unusual stellar populations or by active galactic nuclei contaminating the photometry. Others suggested that star formation in the early universe was simply more efficient than anyone had assumed, converting gas into stars at rates that exceeded the comfortable predictions. Papers flew back and forth. Conferences buzzed with arguments. The standard model bent, but did not break. And then, buried in the same deep field images that revealed those uncomfortably bright galaxies, researchers began noticing something else. Something smaller. Something redder. Something that did not look like any known class of astronomical object. Tiny, compact, extremely red sources. Not extended like galaxies. Not obviously variable like quasars. Not matching the spectral templates of any familiar object in the astronomer's catalogue. They were faint, but not invisible. They were red, but not in the way that dusty galaxies are red. And there were a lot of them. Not one, not a handful. Dozens in every deep image Webb captured. Nobody had predicted them. No model had called for their existence. No simulation had produced anything that looked quite like them. They appeared in survey after survey, field after field, stubbornly present, stubbornly unexplained. Astronomers gave them an informal name that stuck because it captured exactly what they looked like in the images. Little red dots. And with that simple, almost playful name came the beginning of a scientific disruption that is still unfolding today. Because those tiny red specks turned out to be messengers from an era of cosmic history that was not supposed to look like this. They carried information about the first billion years of the universe that contradicted the comfortable expectations built over decades of careful theoretical work. They suggested that something powerful, something compact, something energetically extreme was operating in the young cosmos at scales and abundances that the standard story never accounted for. The comfortable picture of a simple, gradually assembling early universe had just developed its first serious crack. And Webb, the telescope built to confirm our models, was instead pointing directly at evidence that those models might need rewriting from the ground up. What the little red dots actually are, what powers them, and why they exist in such disturbing numbers is a question that would consume the astronomical community for the next several years. The answer, still being assembled from the highest quality data Webb can provide, would prove far stranger and far more unsettling than anyone imagined when those first tiny red specks appeared in the images. The early universe was not supposed to look like this, but it does, and the little red dots are about to tell us why. The first person to notice them probably did not realize what they were looking at. In the earliest deep field images returned by Webb during the second half of 2022, the little red dots were just that, dots. Tiny, almost insignificant pinpricks of reddish light, sitting among thousands of other sources in crowded survey fields. They did not look dramatic. They did not scream for attention the way a blazing quasar or a spectacular gravitational lens does. They were quiet, compact, easy to overlook, and they were everywhere. Understanding why they mattered requires understanding how astronomers work with deep field images, because the process of discovering a new class of object is never as clean as it sounds after the fact. There is no alarm that goes off, no flashing indicator that says new object type detected. What actually happens is far messier and far more human. When Webb stares at a patch of sky for hours or even days, it collects light from objects at vastly different distances. Some sources are relatively nearby galaxies, bright and well resolved. Others are extremely distant, their light having travelled for more than 13 billion years before landing on Webb's detectors. The resulting image is a layered tapestry of cosmic history, with objects from many different epochs sitting side by side in the same frame. A galaxy 1 billion light-years away might sit right next to, in terms of position on the image, an object 13 billion light-years away. They look like neighbours but are separated by 12 billion years of cosmic evolution. The astronomer's first job is to sort this tapestry, to figure out which objects are near and which are far, which are ordinary and which deserve closer attention. This sorting happens through photometry, measuring how bright each source appears through different filters that isolate specific wavelength ranges. Webb carries multiple filter sets on its near-infrared camera, each one transmitting light from a narrow slice of the infrared spectrum while blocking everything else. By comparing the brightness of an object across multiple filters, researchers can construct a rough spectral energy distribution, a profile of how much light the object emits at each wavelength. This profile acts like a fingerprint. Different types of objects produce different profiles. A young star-forming galaxy looks different from an old elliptical galaxy. A dusty galaxy looks different from a clean one. A quasar looks different from everything else. And a red-shifted object looks different from a nearby one, because cosmic expansion has stretched its light toward longer wavelengths, shifting the entire spectral profile in a predictable way. Astronomers have been doing this kind of photometric analysis for decades. They have extensive libraries of template spectra, catalogues of what different types of objects should look like at different redshifts. When a new survey image arrives, the standard procedure is to measure each source's brightness in every available filter and then compare the results to the template library. The software finds the best match. This galaxy is probably a star-forming spiral at redshift 2. That one is probably an elliptical at redshift 1. This faint smudge is probably a very distant galaxy at redshift 8. The process is largely automated, with human researchers reviewing the results, flagging interesting cases and investigating outliers. When scientists began running this standard photometric analysis on Webb's early survey data, a population of sources started standing out. Not because they matched an interesting template, but because they did not match any template at all. They were extremely compact, appearing as unresolved or barely resolved points of light, even in Webb's sharp images. They were notably red, much redder than typical galaxies at similar estimated distances, and their brightness pattern across Webb's filters was unusual. In the shortest infrared wavelengths, corresponding to the rest frame ultraviolet light of the source, they appeared relatively blue, but at longer wavelengths, corresponding to the rest frame optical and near-infrared, they turned sharply and dramatically red. This created a distinctive V-shaped pattern in their spectral energy distribution, bright on the blue end, dropping through the middle wavelengths, then rising steeply toward the red. This V-shaped signature was not something astronomers had seen before in high redshift objects. Known galaxy types did not produce it. Ordinary elliptical galaxies are red, but uniformly so across their optical spectrum. Dusty star-forming galaxies are red, because dust absorbs blue light and re-emits it in the infrared, but their reddening follows a smooth curve that looks nothing like a V shape. Active galactic nuclei powered by accreting black holes can appear red when viewed through thick dust, but even dust-reddened quasars did not match the peculiar spectral shape of these new sources. The template-fitting software would try its best, often assigning these objects wildly different redshifts depending on which templates it was allowed to consider. One run might classify a little red dot as a moderately distant dusty galaxy. Another run, with different template assumptions, might place the same object at a completely different redshift. The fits were poor. The residuals were large. The software was confused because it had never been trained on anything like this. This is where the human element of discovery becomes important. Automated pipelines flag anomalies, but it takes a researcher staring at the data, comparing it to expectations, and recognizing that something genuinely new might be present. In the early months of Webb operations, multiple research groups working independently on different survey fields began noticing the same pattern. Compact, red, V-shaped spectral energy distribution does not match known templates. The convergence of independent groups reaching the same puzzled conclusion simultaneously was itself a signal that these objects were real and not artifacts of any single team's analysis pipeline. The first systematic identification of this population came through several Webb survey programs that were designed to study the early universe. Among the most important was the JWST Advanced Deep Extragalactic Survey known as JADES, which targeted portions of the Hubble Ultra-Deep Field and the good survey regions with Webb's near-infrared camera and near-infrared spectrograph. Another critical program was the Cosmic Evolution Early Release Science Survey, called SEERS, which imaged a wide field in the extended Groth strip. As data from these and other programs accumulated through 2023 and into 2024, the little red dots kept appearing. Not in ones or twos, but in dozens per deep field. Researchers cross-referenced detections across independent surveys and found the same types of objects turning up consistently. Whatever these sources were, they were not flukes of one particular instrument setting or one particular patch of sky. They were a genuine population, distributed across the observable high redshift universe. In March of 2024, the discovery was formally announced in the astrophysical literature. A team led by Jorit Mathi published results from the EAGER and Fresco Webb surveys, identifying what they described as an abundant population of faint active galactic nuclei at redshifts around 5, many of which appeared as compact red point sources. The informal term little red dots, which had already been circulating among researchers in emails, Slack channels, and conference hallways, stuck. It was descriptive, unpretentious, and captured the visual impression of these objects perfectly. The name carried none of the grandeur typically associated with astronomical discoveries. No Greek mythology, no elaborate acronym, just little red dots. And that simplicity belied the depth of the puzzle they represented. As the catalogue grew, a demographic portrait of the little red dot population began to emerge. The objects appeared across a range of redshifts, but they were concentrated between redshifts of roughly 4 and 9. In terms of cosmic time, this corresponds to a window between approximately 600 million and 1.6 billion years after the Big Bang. The majority clustered around redshift 6, meaning most of them existed when the universe was roughly 900 million years old. Before this window, at the very highest redshifts probed by Webb, they were rare or absent, presumably because whatever process created them had not yet begun operating at full capacity. After this window, at redshifts below about 3 or 4, they mostly disappeared. This temporal concentration was itself a clue. Whatever the little red dots were, they represented a phase, not a permanent class of object. They existed during a specific epoch of cosmic history, and then, for reasons that remain debated, they faded away. By the end of 2025, 341 little red dots had been identified and catalogued across multiple Webb surveys. That number alone was striking. These were not rare, exotic outliers, they were common. As Rohan Naidu, an astrophysicist at the Massachusetts Institute of Technology, put it, they appear in every single deep image the telescope takes. You cannot study the early universe with Webb without encountering them. They are woven into the fabric of early cosmic observations as thoroughly as ordinary galaxies. But photographs alone could not reveal what powered these objects. For that, astronomers needed spectra. A spectrum breaks the light from an object into its component wavelengths, like a prism splitting sunlight into a rainbow. Different physical processes leave distinct fingerprints in a spectrum. Hot gas emits light at specific wavelengths determined by the elements present and the temperature and density of the gas. Dust absorbs light at certain wavelengths and re-emits it at others. The velocity of gas produces Doppler shifts that broaden or narrow spectral lines. A single high-quality spectrum can reveal the chemical composition, temperature, density, velocity structure, and energy source of an astronomical object. Without spectra, the little red dots were just coloured dots on an image. With spectra, they could be interrogated. Obtaining spectra of these objects was extraordinarily difficult. The little red dots are faint. They exist at the limits of Webb's observational capability. Collecting enough light to produce a usable spectrum required pointing Webb's near-infrared spectrograph at individual targets for many hours. The process was slow, expensive in telescope time, and technically demanding. Webb's time is among the most competed for resources in all of science. Every hour spent observing a little red dot was an hour not spent observing an exoplanet atmosphere, a nearby galaxy, a gravitational lens, or any of the thousands of other compelling targets in the observing queue. Researchers had to write persuasive proposals justifying why these mysterious red dots deserved precious telescope time over other worthy projects. The fact that multiple independent teams succeeded in winning that time speaks to how seriously the community took the puzzle. When the first spectra began arriving, the researchers who had fought for the telescope time gathered around their screens expecting to see something that fit into an existing category. That is how spectroscopy usually works. You have a mysterious object. You obtain its spectrum. The spectrum reveals it to be a dusty galaxy, or a distant quasar, or an unusual star. Mystery solved, paper published, onward to the next target. The little red dots refused to cooperate. The first thing the spectra showed was broad emission lines, particularly in the hydrogen-Balmer series. The most prominent of these, the hydrogen alpha line, appeared significantly broadened, with widths corresponding to velocities of several thousand kilometers per second. In conventional astrophysics, broad emission lines of this type are a hallmark of active galactic nuclei. Gas orbiting close to a supermassive black hole moves at tremendous speeds, and the Doppler effect broadens the emission lines it produces. When astronomers see broad hydrogen lines in a distant object, the default interpretation is that they are looking at gas swirling around a feeding black hole. So the first reaction among many researchers was straightforward. The little red dots are probably some kind of active galactic nucleus, probably obscured by dust. The mystery seemed halfway solved, but then the problems started accumulating. And they accumulated fast. Standard active galactic nuclei, even those heavily obscured by dust, produce strong X-ray emission. The intense radiation from the accretion disk around a black hole generates copious high-energy photons that penetrate most intervening material. X-rays are difficult to block. Even thick columns of dust and gas that absorb optical and ultraviolet light allow a significant fraction of X-ray photons to escape. This is why X-ray observations have been one of the most reliable tools for identifying active galactic nuclei throughout the history of extragalactic astronomy. If something is powered by a feeding black hole, it should glow in X-rays. Multiple teams used the Chandra X-ray Observatory and other X-ray facilities to search for X-ray emission from little red dots. They found almost nothing. The X-ray emission was extremely weak, orders of magnitude below what standard active galactic nucleus models predicted. This was deeply puzzling. If these objects were powered by accreting black holes, where were the X-rays? Researchers stacked the X-ray data from dozens of little red dots, combining their faint signals to increase sensitivity. Still nothing significant. The X-rays were missing. Radio emission told a similar story. Active galactic nuclei frequently produce radio jets, powerful streams of charged particles launched from the vicinity of the black hole at nearly the speed of light. These jets emit radio waves detectable by ground-based radio telescopes. Searches for radio emission from little red dots came up largely empty. Whatever was happening inside these objects, it was not producing the standard observational signatures associated with black hole accretion. The broad emission line said black hole. The missing X-rays and radio emission said not a black hole. Both statements came from the same objects. The spectral shape added another layer of confusion. Many little red dots showed a feature called a Balmer break, and this feature deserves careful explanation because it became one of the most hotly debated aspects of the entire mystery. A Balmer break is a sharp drop in brightness at a specific wavelength, roughly 3,646 angstroms in the rest frame, corresponding to the ionization edge of hydrogen. Below this wavelength, hydrogen atoms can absorb photons efficiently. Above it, they cannot. In normal galaxy spectra, a Balmer break indicates the presence of a significant population of older stars, typically A-type stars that have been shining for several 100 million years or more. Young, recently formed stellar populations do not produce a strong Balmer break because their light is dominated by hot blue stars that overwhelm the signature. Old populations do produce one because the hot stars have died, and the remaining cooler stars create the characteristic absorption pattern. This is why finding a strong Balmer break in a little red dot at redshift 7 was so jarring. Redshift 7 corresponds to a time when the universe was only about 700 million years old. For an object at that epoch to show a prominent Balmer break, it would need to contain a substantial population of stars that had already been burning for several 100 million years. That meant those stars had to have formed when the universe was only 200 or 300 million years old, deep in the cosmic dark ages, at a time when the standard model expected star formation to be just barely beginning in the most extreme environments. Finding a Balmer break at redshift 7 was like examining what should be a newborn infant, and discovering it already has grey hair. The age signatures did not match the youth of the universe at that moment. Some researchers interpreted this as evidence that the little red dots were not active galactic nuclei at all, but rather compact galaxies packed with stars at extraordinary densities. Perhaps they had formed their stars in an intense early burst and then aged rapidly. This interpretation had its own problems. If the little red dots were purely star-forming galaxies, their implied stellar masses were uncomfortably large for their cosmic epoch. Some estimates suggested stellar masses exceeding 1 billion solar masses, crammed into regions only a few hundred light-years across. To put that in perspective, the Milky Way contains roughly that many solar masses of stars, spread across a disk 100,000 light-years wide. Compressing a comparable stellar mass into a region 1,000 times smaller would create stellar densities far exceeding anything observed in the local universe. Stars would be packed so closely that the night sky on a hypothetical planet in such a galaxy would blaze with the light of millions of nearby suns. The most extreme cases implied surface brightness levels that seemed physically implausible, pushing against fundamental limits on how much light a given volume of space can produce before radiation pressure disrupts the structure. And so the astronomical community found itself staring at objects that did not fit neatly into any existing category. They had broad emission lines, like active galactic nuclei, but lacked the X-ray and radio signatures. They had Balmer breaks like mature stellar populations but implied masses and densities that stretched credulity. They were compact like point sources but existed at distances where even Webb could not resolve their internal structure in detail. They were red in a way that did not match known dusty galaxies, and blue in a way that did not match known quasars. They were abundant in a cosmic epoch, where neither explanation was easy to accommodate. What followed was a period of intense and sometimes contradictory scientific output that lasted through the second half of 2023 and into early 2024. Different research groups, each working with spectra of one or two or perhaps a handful of little red dots, published papers championing different explanations. The field was not converging, it was fragmenting. One team would obtain a spectrum of a particularly bright little red dot and find strong, broad emission lines with no detectable Balmer break. Their paper would argue confidently that the object was a dust-obscured active galactic nucleus, a feeding black hole hidden behind a thick screen of gas and dust that absorbed the X-rays and reddened the optical light. The missing X-rays were a problem, they would acknowledge, but perhaps the obscuring column was unusually dense, thick enough to absorb even the hardest X-ray photons. Their conclusion would be that little red dots were simply a new flavor of obscured quasar, unexpected in such numbers at high redshift, but explicable within the existing active galactic nucleus framework. Meanwhile, another team would obtain a spectrum of a different little red dot, this one showing a prominent Balmer break and relatively narrow emission lines. Their paper would argue with equal confidence that this object was clearly a compact star-forming galaxy, not an active galactic nucleus at all. The Balmer break proved the presence of an evolved stellar population. The narrow lines came from ionized gas heated by young stars, not by black hole accretion. The redness came from dust produced by the rapid star formation. Their conclusion would be that little red dots were ultra-compact starburst galaxies, a new class of early star-forming system with properties unlike anything in the local universe. A third group might obtain spectra of two little red dots that looked different from each other. One matched the active galactic nucleus picture, the other matched the compact galaxy picture. Their paper would propose that the little red dot population was actually a mixture of two distinct types of objects that happened to look similar in broadband photometry but were physically unrelated. The V-shaped spectral energy distribution might arise from different physical causes in different objects. Perhaps some were black holes and some were galaxies, and the confusion arose from lumping them together under a single label. Still, other researchers proposed hybrid models where a single object contained both an accreting black hole and an intense starburst, the two components contributing different fractions of the observed light at different wavelengths. In these models, the broad lines came from the black hole component, while the Balmer break came from the stellar component. The challenge was making the two components fit together self-consistently, with the right luminosity ratio, the right spectral shape, and the right spatial configuration, without violating any observational constraints. Some hybrid models worked reasonably well for individual objects, but failed when applied to the broader population. The problem was that everyone was working from small, heterogeneous samples. One group might have spectra from 3 little red dots in the JADES field. Another might have 2 from the Sears field. A third might have one particularly bright example from a different survey entirely. Each team naturally interpreted their data in the context of the models they knew best. Active galactic nucleus specialists saw black holes, galaxy evolution experts saw compact galaxies. Theorists working on exotic stellar physics saw opportunities for novel objects. Without a large, uniformly selected sample observed with consistent methods, there was no way to determine which interpretation applied to the majority of the population. The situation resembled the old parable of blind men and an elephant. Each group was touching a different part of the same creature and reaching different conclusions about what they had found. One felt a trunk and declared it a snake. Another felt a leg and declared it a tree. The disagreements were genuine and scientifically motivated, not mere ego or stubbornness. The data available to each group genuinely supported different interpretations. What the field needed was not another paper about 1 or 2 objects. It needed a systematic census, a program that would observe a large representative sample with uniform methods and analyze them all consistently. It needed someone to step back and look at the whole elephant. The RUBIES program was designed to be exactly that census. RUBIES, which stands for Red Unknowns, Bright Infrared Extragalactic Survey, was a dedicated Webb spectroscopic program led by Anna de Graaf and Gabriel Brammer at the Max Planck Institute for Astronomy and the University of Copenhagen. The program specifically targeted very red sources identified in Webb imaging, collecting deep spectra for hundreds of objects across two well-studied extragalactic fields, the ultra-deep survey field and the extended growth strip. Rubies was not a casual effort. It represented a major investment of Webb observing time, designed from the outset to produce the systematic spectroscopic census that the field desperately needed. Rather than studying one or two interesting objects in detail, Rubies cast a wide net, gathering spectra for a large statistical sample that could reveal population-level properties invisible in any individual observation. The Rubies results, published through 2025, painted an increasingly complex picture. The team found that the little red dot population was not perfectly uniform. Some objects showed strong broad emission lines with widths exceeding 4,000 kilometers per second. Others had weaker or absent broad components. Some displayed prominent Balmer breaks, others did not. The amount of reddening varied from source to source. This diversity suggested that little red dots might not all be identical objects. They might represent a family of related phenomena, or perhaps the same type of object viewed at different evolutionary stages or from different angles. The Rubies census also found that the spectroscopic properties of many little red dots did not cleanly match models of either pure star-forming galaxies or pure active galactic nuclei. Many sources seem to require some combination of both components, or perhaps an entirely new physical model that had not yet been developed. One particularly illuminating result from the Rubies program was the discovery that the little red dot population showed much lower levels of hot and cold gas than theoretical models predicted for either interpretation. If these objects were active galactic nuclei, standard models expected significant reservoirs of warm molecular gas fueling the accretion process. If they were starburst galaxies, models expected even larger gas reservoirs feeding the intense star formation. Rubies found neither. The gas content was lower than either scenario comfortably predicted, pointing away from both conventional explanations and hinting that something more unusual was at work. Among the individual objects in the Rubies catalogue, several stood out as particularly challenging to existing theory. The source designated Rubies Blang 1 proved to be an unusually bright little red dot at a redshift of 3.1. Its spectrum displayed a striking combination of features that should not coexist under conventional models. It showed a blue ultraviolet continuum, meaning the shortest wavelengths of its light were genuinely blue, not reddened. It showed broad emission lines, with widths around 4,000 kilometers per second, and it showed a clear Balmer break alongside a red continuum extending out to rest frame 4 micrometers, as measured by Webb's mid-infrared instrument. This combination was extraordinary. The blue ultraviolet light suggested an unobscured energetic source. The broad lines suggested high-velocity gas. The Balmer break suggested an older stellar population or a very specific physical mechanism for producing the break. And the red continuum extending deep into the mid-infrared suggested something was reprocessing radiation at longer wavelengths. No single standard model could produce all of these features simultaneously. Rubies Blang 1 became a key benchmark object, a system whose properties any successful theory would need to explain. The most optically luminous little red dot found by Webb resided in the Abell 2744 galaxy cluster field. This object was remarkable not only for its brightness, but for what that brightness implied about the energy source powering it. At the luminosities observed, the energy output exceeded what even the most extreme star formation scenarios could plausibly produce in such a compact volume. The sheer amount of light radiating from this tiny source pushed against physical limits, demanding an explanation that went beyond ordinary astrophysics. But no object in the Rubies sample attracted more attention than the cliff. Designated informally for the sheer precipitousness of its spectral drop, this little red dot displayed one of the most extreme Balmer breaks ever measured in any astronomical object at any distance. The sharpness of the spectral feature was so severe that it resembled a cliff edge when plotted on a graph, brightness holding steady on one side of the break wavelength and then plunging almost vertically on the other. When the Ruby's team attempted to fit the cliff spectrum with standard models, neither the star-forming galaxy template nor the active galactic nucleus template could reproduce the observations. The Balmer break was too strong, the emission lines too broad, the overall spectral shape too peculiar. The cliff resisted classification. It sat at the extreme edge of the little red dot population, daring theorists to explain it. As we will see, the challenge it posed would push researchers to propose entirely new categories of astrophysical objects. Meanwhile, observations with Webb's mid-infrared instrument, known as MIRI, and with the Atacama Large Millimeter Array, known as ALMA, added further constraints. MIRI observations probed the rest frame near-infrared light of little red dots, sampling wavelengths that are sensitive to different physical components than the shorter wavelength data from Webb's near-infrared instruments. Some MIRI results suggested that the red optical continuum of little red dots was better fit by stellar-dominated models than by active galactic nucleus models, complicating the black hole interpretation. ALMA observations search for cold dust and ionized carbon emission, which would indicate significant star formation. Several studies, including one published in early 2025, examining 2 little red dots at redshifts above 7, found no detectable ionized carbon or cold dust continuum emission. This was difficult to reconcile with the dusty star-forming galaxy hypothesis, since galaxies forming stars at the rates implied by the little red dot luminosities should produce significant amounts of dust detectable by ALMA. Each new observation seemed to close one door while opening another. The little red dots refused to be pinned down. What made this scientific impasse particularly unsettling was not the existence of ambiguous objects. Astronomy is full of sources that resist easy classification. What made the little red dots genuinely disturbing was their combination of 3 properties taken together. First, they were abundant, hundreds of them in every deep survey field. Second, they were concentrated in the first billion years of cosmic history. Third, whatever physical process powered them, whether black hole accretion, intense star formation, or something else entirely, was operating with an efficiency and a prevalence that no standard model of early universe evolution had anticipated. If the little red dots were active galactic nuclei, then the early universe contained far more feeding supermassive black holes than anyone had predicted. The number density of active black holes in the first billion years would need to be revised dramatically upward, raising immediate questions about how so many black holes formed and grew so quickly. The Eddington limit would become an even tighter constraint. Either the black holes started from heavier seeds than standard stellar remnants, or they grew through super Eddington accretion episodes that somehow circumvented the usual radiation pressure barrier, or both. If the little red dots were compact star-forming galaxies, then the early universe was producing stars at extraordinary rates in extraordinarily dense configurations. The total stellar mass budget of the early cosmos would need to be revised upward, challenging models of how efficiently gas converts into stars at high redshift. The implied star formation efficiencies would exceed theoretical limits derived from our understanding of gas physics and feedback processes in galaxies. And if the little red dots were something in between, a hybrid population containing both black hole accretion and star formation, or something entirely new, then the theoretical challenge was even greater. The standard framework had no ready-made category for such objects. New models would need to be built from scratch. The scientific community responded with the intensity that only a genuine puzzle can generate. By the end of 2025, little red dots had become one of the most actively researched topics in extragalactic astronomy. Hundreds of papers had been published. Competing theoretical frameworks jostled for dominance at conferences. Observing proposals flooded the Webb scheduling committees, each one promising to crack the mystery with just a few more hours of telescope time. The little red dots had gone from unnamed curiosities in the background of survey images to one of the defining scientific challenges of the Webb era. As Jenny Green, an expert in supermassive black holes and galaxy evolution at Princeton University, reflected, Webb is a $10 billion space mission, and you hope to find things that are truly unknown. The little red dots had delivered exactly that, something that looks a bit like a galaxy, a bit like a black hole, and a bit like a star, with experts from all these communities now trying to contribute their insights. And the stakes were enormous, because if the black hole interpretation held up, even partially, it would mean something profound about the nature of the early universe. It would mean that the young cosmos was not the quiet, gradually assembling nursery that decades of theoretical work had described. It would mean that powerful, compact, energetically extreme systems were common features of the first billion years. It would mean that the engines of destruction that today sit quietly at the centers of massive galaxies were already operational, already feeding, already shaping their environments in an epoch when the universe was supposed to be barely waking up. The little red dots had been found. Their basic observational properties had been catalogued. Their spectra had been collected and argued over. But the central question remained unanswered. What were they really? And the answer to that question, still being assembled from the most demanding observations Webb can deliver, would carry implications that extended far beyond the classification of a few hundred faint red specks. Because if the leading interpretation was correct, the little red dots were not just unusual objects. They were evidence that the early universe had been doing something extraordinary. Something fast. Something violent. Something that the comfortable models never saw coming. What comes next belongs to the theorists, the modelers, and the teams pushing Webb's instruments to their absolute limits. Because the data they have gathered since 2025 does not just deepen the mystery, it begins, for the first time, to resolve it. And the resolution is more disturbing than the mystery itself. In January of 2026, a paper appeared in the journal Nature that changed the trajectory of the entire debate. A team led by Darak Watson at the University of Copenhagen had done something deceptively simple. They had taken the highest quality spectra available for a sample of little red dots, spectra collected by Webb's near-infrared spectrograph with long exposure times and excellent signal-to-noise ratios, and they had looked more carefully than anyone before at the shape of the broad emission lines. What they found overturned one of the key assumptions that had guided the field for nearly 2 years. The broad hydrogen lines in little red dots, the lines that had prompted comparisons to active galactic nuclei since the earliest spectroscopic observations, were not broadened by the mechanism everyone had assumed. As we already know, the standard interpretation of those broad lines was straightforward. Fast-moving gas orbiting close to a black hole produces Doppler-broadened emission. The wider the line, the faster the gas. The faster the gas, the heavier the black hole. This relationship is how astronomers weigh distant black holes. It is one of the most trusted tools in extragalactic astronomy. Measure the line width, calculate the orbital velocity, infer the mass. Previous estimates using this standard method had assigned enormous masses to the black holes powering little red dots. Some calculations yielded black hole masses of 100 million to 1 billion solar masses. These numbers were staggering for objects existing in the first billion years of cosmic history and contributed significantly to the sense of crisis surrounding the little red dots. Black holes that massive, that early, were nearly impossible to produce through conventional growth channels, even under the most generous assumptions about seed masses and accretion rates. Watson's team showed that the line broadening was not primarily caused by Doppler motion at all. Instead, it was caused by electron scattering. Electron scattering occurs when photons pass through a dense medium of free electrons. Each time a photon encounters an electron, it bounces off in a slightly different direction with a slightly different energy. If the photon passes through a thick enough column of electrons, the cumulative effect of many scattering events broadens the spectral line, smearing it out in wavelength space in a way that can mimic the appearance of Doppler broadening. The two effects produce superficially similar line profiles, but they arise from completely different physical processes. Doppler broadening requires fast-moving gas. Electron scattering requires dense ionized gas, but not necessarily gas moving at extreme velocities. The distinction matters enormously because it changes the inferred black hole masses by orders of magnitude. When the Watson team reanalyzed the spectra under the electron scattering interpretation, they found that the intrinsic emission line cores were narrow, not broad. The narrow cores implied gas velocities consistent with much smaller black holes. The revised mass estimates came in at roughly 100,000 to 10 million solar masses. That is approximately 100 times less massive than the previous estimates based on the Doppler assumption. This was a transformative result. It did not eliminate the black hole interpretation. In fact, it strengthened it in certain respects. The extremely high electron column densities required to produce the observed scattering could only be explained by extraordinarily dense, compact gas structures. The team calculated that the scattering medium had to be confined to a region measured in light days across, an astonishingly small volume on cosmic scales. When you combine this compactness with the high luminosities of the little red dots, the only known physical mechanism capable of powering the observed emission was accretion onto a supermassive black hole. Stellar processes alone could not generate enough energy in such a tiny volume. The picture that emerged was vivid and specific. The little red dots were young black holes, far less massive than previously believed, embedded in extraordinarily dense cocoons of ionized gas. These cocoons were not passive shrouds, they were active participants in the system's behavior. The black hole at the center was accreting gas from the cocoon, generating intense radiation that ionized the surrounding material and heated it to extreme temperatures. The radiation passed outward through the dense ionized gas, where electron scattering broadened the emission lines and reprocessed high-energy photons into the lower-energy optical and ultraviolet light that Webb detects after cosmological redshifting into the infrared. The cocoon absorbed the X-rays that would normally escape from an active galactic nucleus, explaining the baffling absence of X-ray emission that had troubled researchers for years. The dense gas trapped the high-energy radiation, converting it into the characteristic red glow that gave these objects their name. Watson described the model in strikingly clear terms. The little red dots are young black holes, roughly 100 times less massive than previously believed, enshrouded in a cocoon of gas which they are consuming in order to grow larger. The process generates enormous heat, which shines through the cocoon. This radiation through the cocoon is what gives little red dots their unique red color. The model elegantly unified several previously contradictory observations. The broad lines, the extreme redness, the compact morphology, the missing X-rays, the high luminosities, all found a coherent explanation within a single physical framework. But the Watson team's paper was not the only major theoretical development in early 2026. Almost simultaneously, a team led by Fabio Piccucci at the Harvard-Smithsonian Center for Astrophysics published a study on the preprint server, ArgZeev, arguing that the little red dots could be explained as direct collapse black holes. Direct collapse is one of the most theoretically important and observationally elusive mechanisms proposed for forming heavy black hole seeds in the early universe. The standard pathway for black hole formation begins with a massive star. The star exhausts its nuclear fuel, its core collapses, and a stellar mass black hole forms with perhaps 10 to 100 solar masses. This seed then grows over time through accretion. But as discussed earlier, Eddington-limited growth from such a small seed cannot easily produce the supermassive black holes observed in the first billion years. The timeline is too short. Direct collapse offers a shortcut. Under very specific conditions in the early universe, a massive cloud of primordial gas could collapse directly into a black hole without first forming stars. This requires the gas cloud to avoid fragmenting into smaller clumps, which would normally lead to star formation. If the cloud is exposed to a strong background of ultraviolet radiation from nearby galaxies, this radiation can suppress the formation of molecular hydrogen, which is the primary coolant that allows gas clouds to fragment. Without efficient cooling, the the cloud remains hot and collapses monolithically, forming a single massive object that quickly becomes a black hole with a mass of 10,000 to 100,000 solar masses. This heavy seed can then grow to supermassive scales through Eddington-limited accretion within the available cosmic time. Direct collapse black holes had been theoretically predicted for years but never observationally confirmed. They were expected to be rare, forming only in special environments where the conditions for suppressed cooling were met. Finding them would be a major breakthrough because it would confirm a key pathway for explaining how the earliest supermassive black holes came to exist. Pacucci's team used sophisticated radiation hydrodynamic simulations to model the formation and early growth of direct collapse black holes, tracking both the infall of gas onto the black hole and the effects of the radiation produced by the accretion process on the surrounding environment. They then converted their simulation outputs into synthetic observations, predicting what these objects would look like if observed by Webb. The match to the actual little red dot data was remarkably good. The simulations reproduced the compact morphology, the characteristic redness, the broad emission lines, the weak X-ray emission, the spectral shape, and critically, the abundance and redshift distribution of the observed population. Pacucci summarized the implications directly. The results suggested that Webb was witnessing exactly the long-sought phase of massive black hole seed formation through direct collapse. If correct, it would represent a major breakthrough, demonstrating that the earliest black holes formed efficiently and early, and that Webb had finally opened a direct observational window onto their birth. The direct collapse scenario carried a specific and important implication. It meant that the early universe was not merely accommodating a few exceptional black holes through unlikely circumstances. It was systematically producing heavy black hole seeds through a physical process that operated efficiently across many environments. The little red dots were not flukes. They were products of a formation channel that the universe exploited widely during its first billion years. And then came yet another interpretation, from yet another direction, adding a third layer to an already rich theoretical landscape. In January of 2026, at the 247th meeting of the American Astronomical Society, a team led by Diptijoti Nandal at the Harvard-Smithsonian Center for Astrophysics presented results arguing that some little red dots might not be black holes at all, at least not yet. They might be supermassive stars. Supermassive stars are a theoretical class of objects predicted to exist in the early universe but never directly observed. These are not merely very large stars like the blue supergiants found in nearby galaxies. They are fundamentally different objects, containing tens of thousands to hundreds of thousands of solar masses in a single stellar body. They are thought to form in the same dense, hot environments that produce direct collapse black holes, and in many models they represent an intermediate stage. A massive gas cloud collapses, forms a supermassive star. The star burns through its nuclear fuel in a cosmically brief period, perhaps a few million years, and then collapses entirely into a black hole. Nandal's team compared theoretical spectra of supermassive stars to the observed spectra of little red dots, and found striking agreement across a wide range of stellar masses. The spectral signatures, including the broad emission features, the Balmer break, and the characteristic reddening, could all be reproduced by models of supermassive stars in their final evolutionary stages. The luminosities match for the most massive models. The team argued that if their interpretation was correct, Webb was not just seeing young black holes. It was seeing the objects that were about to become black holes. It was witnessing the birth of heavy seeds in real time. Nandal captured the significance of this possibility with precision. If the interpretation was right, scientists were not merely inferring that heavy black hole seeds must have existed. They were watching some of them being born. That would provide a much stronger observational foundation for understanding how the universe's supermassive black holes and galaxies grew. 3 interpretations, 3 research groups, 3 distinct physical models, and yet all 3 pointed in the same deeply uncomfortable direction. Whether the little red dots were young black holes shrouded in dense gas cocoons, or direct collapse black holes freshly formed from monolithic gas cloud collapse, or supermassive stars on the verge of collapsing into black holes, the conclusion was structurally identical. The early universe was producing powerful, compact, energetically extreme systems on a scale and with an efficiency that the standard gradual assembly picture never anticipated. The specific mechanism mattered for the details of black hole formation theory, but the broad implication was the same regardless of which model ultimately proved correct. Something intense was happening in the first billion years, something widespread, something that could not be dismissed as a handful of statistical outliers. The sheer number of little red dots amplified this discomfort. 341 confirmed objects across multiple survey fields is not a small sample. Extrapolating from the surveyed areas to the full sky yields estimates of hundreds of thousands or even millions of similar objects across the observable universe at these redshifts. If even a significant fraction of them harbor growing black holes, the early universe contained a far larger population of active black hole systems than any pre-Webb model predicted. The number density of accreting black holes in the first billion years would need to be revised upward by factors that challenge the most flexible versions of the standard model. The overmassive black hole problem added another dimension to the tension. Even with the downward revision of black hole masses provided by the Watson team's electron scattering analysis, many little red dots still appeared to contain black holes that were disproportionately massive compared to their host galaxies. In the local universe, supermassive black holes and their host galaxies follow a well-established scaling relation. The mass of the black hole correlates tightly with the mass of the galaxy's central bulge. This correlation suggests that black holes and galaxies grow together over cosmic time, regulating each other through feedback processes. But in many little red dots, the black hole appeared to represent a far larger fraction of the total system mass than the local scaling relations would predict. Some objects seem to be almost entirely black hole, with minimal surrounding stellar mass. These have been described as naked black holes, systems where the black hole dominates and the galaxy is either absent or embryonic. This inversion of the expected relationship carried profound implications. If black holes in the early universe were overmassive relative to their galaxies, it suggested that black holes might grow first, and galaxies might assemble around them later. This would reverse the conventional understanding of cosmic structure formation, in which galaxies form first and black holes grow gradually within them. The little red dots were hinting at a universe where the engines of destruction preceded the cities they would eventually inhabit. The Balmer break puzzle remained unresolved even after these theoretical advances. The extreme case of the cliff, with its dramatic spectral drop, pushed the boundaries of every proposed model. The Watson team's cocoon model could accommodate moderate Balmer, breaks through the reprocessing of radiation in the dense gas envelope, but the cliff's break was more extreme than the cocoon model easily explained. The Ruby's team, led by de Graaf, proposed that the cliff might represent an entirely new type of object, a black hole star, in which a black hole is embedded within an extended gaseous stellar-like envelope. In this model, the black hole accretes from the envelope, while the envelope itself radiates like an extremely unusual star, producing the observed Balmer breakthrough physical processes distinct from either a normal stellar population or a standard accretion disk. The black hole star concept was speculative and unproven, but it illustrated a broader point about the state of the field. The little red dots had driven theorists to the edge of known astrophysics. Standard models of galaxies, standard models of active galactic nuclei, standard models of stellar evolution, none of them could fully account for all the observed properties of these objects. Something new was needed. Whether that something new was a minor adjustment to existing frameworks or a fundamentally novel category of astrophysical object remained an open question. The missing X-ray emission continued to provide one of the strongest constraints on any theoretical model. Multiple deep X-ray observations using Chandra, stacking the signals from dozens of little red dots to maximize sensitivity, failed to produce significant detections. The upper limits on X-ray luminosity were far below what standard accretion models predicted. Both the cocoon model and the direct collapse model offered explanations for this. In the cocoon scenario, the dense ionized gas absorbs X-rays before they can escape. In the direct collapse scenario, the extremely dense gas environment surrounding the newly formed black hole similarly traps high-energy radiation. The supermassive star model avoided the X-ray problem entirely because the object was not yet a black hole, and therefore was not producing accretion-powered X-ray emission. All three models could accommodate the X-ray constraint, but through different physical mechanisms, making it difficult to use X-ray non-detections alone to distinguish between them. The absence of cold dust and molecular gas emission in many little red dots, as revealed by ALMA observations, added yet another constraint. Studies published in 2025 found no detectable ionized carbon or cold dust continuum emission in several little red dots at redshifts above 7. This argued against the dusty star-forming galaxy interpretation, since galaxies forming stars at the rates implied by the little red dot luminosities should produce significant amounts of dust. The ALMA non-detections favoured models in which the reddening was produced by dense gas rather than by dust grains, which was more consistent with the black hole cocoon and direct collapse scenarios. Variability studies provided another line of evidence. A team analysing multi-epoch Webb images of approximately 300 little red dots found tentative evidence for brightness variations in a minority of sources. Active galactic nuclei are expected to vary in brightness over timescales of months to years as the accretion rate onto the central black hole fluctuates. Star-forming galaxies do not vary on these timescales. The detection of variability in some little red dots supported the black hole interpretation, although the signal was weak and the fraction of variable sources was lower than expected for a population dominated by traditional active galactic nuclei. A particularly intriguing discovery came from observations of an individual little red dot designated a 2744-QS01, located in the Abell 2744 galaxy cluster field at a redshift of 7.04. This object was described as a naked black hole because it appeared to have very few stars in its vicinity. It was almost pure black hole accretion emission with negligible surrounding stellar mass. If confirmed, this object represented the most extreme example of the overmassive black hole phenomenon, a black hole existing essentially alone in the early universe, without the galaxy that was supposed to come first. Another notable object, designated J1007_AGN, was found at redshift 7.3, embedded within an overdensity of 8 nearby galaxies. This clustering suggested that the little red dot inhabited a region of enhanced matter density, exactly the type of environment where theoretical models predicted heavy black hole seeds might preferentially form. The environmental context supported the direct collapse scenario, which requires specific conditions including strong ultraviolet radiation fields typically found near other star-forming systems. Taken together, the observational evidence accumulated through 2025 and early 2026 painted a picture that was increasingly coherent but deeply uncomfortable. The little red dots were most likely powered by accreting black holes. The black holes were less massive than initially estimated, but still remarkably substantial for their cosmic epoch. They were embedded in dense gas environments that obscured standard diagnostic signatures and reprocessed their radiation into the distinctive red spectral shape that Webb detected. They existed in large numbers across the first billion years of cosmic history, and they challenged the standard timeline of cosmic structure formation in a way that could not be dismissed or minimized. The discomfort was not about a single anomalous object. It was about a pattern, a population, a systematic feature of the early universe that the pre-Webb theoretical framework had no room for. The early cosmos was building black holes, growing them, feeding them, wrapping them in dense cocoons of superheated gas, and doing all of this more abundantly and more efficiently than any mainstream model had predicted. The little red dots were not exceptions to the rule. They were beginning to look like the rule itself, a previously hidden but fundamental stage in the early universe's assembly of the structures that would eventually become the galaxies, black holes, and cosmic web we observe today. And the question that hung over all of this work, the question that made the little red dots genuinely frightening in a scientific sense, was not what they were. That question was being answered piece by piece, spectrum by spectrum. The more unsettling question was what their existence implied about the universe as a whole. If the cosmos was capable of this much energetic violence this early in its history, what did that say about the fundamental processes governing structure formation? What did it say about the seeds of the first black holes? What did it say about the transition from the cosmic dark ages to the luminous universe we inhabit today? Those questions belong to the final stretch of this story, and the answers emerging from the latest data do not offer the reassurance that many scientists were hoping for. The little red dots do not exist in isolation. They are one piece of a pattern that has been building since Webb's first observations, and it is the pattern, not any single discovery, that carries the real weight of scientific unease. To understand why the little red dots matter beyond their own fascinating astrophysics, you have to step back and see what else Webb has revealed about the first billion years of cosmic history, because the little red dots are not the only things that should not be there. Within months of beginning scientific operations, Webb identified galaxies at redshifts of 10, 12, and possibly higher that appeared far more luminous and far more massive than the standard model of cosmology predicted. These were not little red dots. They were extended, resolved sources with spectral signatures consistent with established stellar populations. But they were too bright, too massive, too mature for their age. A galaxy observed at redshift 12 is being seen as it existed roughly 350 million years after the Big Bang. At that point in cosmic history, the standard model expected only the most primitive protogalactic structures to exist. Tiny, irregular clumps of gas, with a few million young stars at most. What Webb found instead were objects with estimated stellar masses of several hundred million to over a billion solar masses, galaxies that appeared to have been forming stars vigorously for tens or even hundreds of millions of years before the moment we were observing them. This was the first shock. Galaxies were assembling faster than the models allowed. Star formation in the early universe was proceeding with an efficiency that exceeded theoretical predictions based on our understanding of how gas cools, fragments, and collapses into stars within dark matter halos. The standard framework assumed that only a small fraction of available gas would convert into stars during the early epochs, because feedback processes like radiation pressure, supernova explosions, and turbulence would slow the process down. Webb suggested that the actual conversion efficiency was significantly higher, at least in some environments. Then came the discovery of surprisingly mature stellar populations at high redshift. Some early galaxies observed by Webb showed spectral signatures consistent with stars that had been evolving for several hundred million years. These old stars coexisted with younger populations in the same galaxy, indicating that star formation had begun very early and continued over extended periods. Finding chemically enriched, evolved stellar populations at redshifts of 8 or 9 meant that the first significant wave of star formation must have occurred at redshifts of 15 or higher, well into the cosmic dark ages, earlier than most models had placed it. Then came the black holes. Even before the little red dots were formally identified as a population, Webb had confirmed the existence of actively accreting supermassive black holes at redshifts exceeding 7. These were not always associated with little red dots. Some appeared as more traditional active galactic nuclei, quasar-like objects with luminosities consistent with black hole masses of tens of millions to hundreds of millions of solar masses. Their existence at such early times compounded the tension that had already been building from pre-Webb quasar discoveries. The Eddington limit problem, the difficulty of growing a small seed black hole to supermassive scales within the available cosmic time, became more acute as Webb kept finding more black holes at higher and higher redshifts. And now, on top of all of this, came the little red dots. Hundreds of compact, energetically extreme objects populating the first billion years of cosmic history. most likely powered by accreting black holes embedded in dense gas cocoons, existing in numbers that no model had anticipated. Each of these discoveries individually could perhaps be accommodated by stretching the standard model. Maybe star formation efficiency was a bit higher than assumed. Maybe black hole seeds were a bit heavier than the standard stellar remnant pathway produced. Maybe feedback processes were a bit less effective in certain early environments. Each individual tension could be addressed with a targeted adjustment, but the little red dots made the situation qualitatively different because they added not just another anomaly but a systematic population that connected all the other anomalies into a single, coherent, and deeply uncomfortable narrative. That narrative goes like this. The early universe was not simple. It was not dim. It was not gradually assembling its structures over billions of patient years. Instead, the first billion years of cosmic history were a period of extraordinary productivity and violence. Stars formed faster than expected. Galaxies assembled sooner than predicted. Black holes appeared earlier and in greater numbers than any mainstream model accommodated. And the little red dots, those hundreds of compact red specks scattered across every deep web image, were perhaps the most vivid evidence of this accelerated cosmic adolescence. They were the smoking guns of an early universe that was building powerful engines of destruction at a pace that made the comfortable story untenable. This is what the fear in the title actually means. It is not a fear of monsters lurking in space. It is not a fear that the universe is dangerous in some personal sense. It is the specific, technical, deeply felt scientific discomfort that arises when a foundational model begins to crack under the weight of evidence it was not designed to explain. Cosmologists spent decades constructing a picture of cosmic evolution that was self-consistent, mathematically elegant, and supported by multiple independent lines of evidence. The lambda-cold dark matter model, combined with standard theories of star formation and black hole growth, told a story that matched the cosmic microwave background, the large-scale structure of the galaxy distribution, the abundance of light elements, and the observed properties of nearby galaxies. It was one of the great achievements of modern physics. And now Webb was showing that the opening chapters of that story might be wrong. The implications cascade through multiple branches of astrophysics. Consider what it means if heavy black hole seeds form through direct collapse in the early universe. The direct collapse scenario requires very specific conditions. A massive gas cloud in a region bathed in strong ultraviolet radiation that suppresses molecular hydrogen cooling. These conditions were thought to be relatively rare, occurring only in special environments where neighboring galaxies provided the necessary radiation field. If direct collapse produced the little red dots, and if there are hundreds of thousands or millions of similar objects across the observable universe at those redshifts, then either the conditions for direct collapse were far more common than theorists assumed, or the formation process is less constrained than current models require. Either way, the standard predictions for the abundance of heavy black hole seeds need dramatic revision. This revision has consequences for every supermassive black hole in the universe today, including the 4 million solar mass black hole sitting at the center of our own Milky Way. Every supermassive black hole had to start somewhere. It had to begin as a seed and grow over cosmic time through accretion and mergers. If the seeding process was far more efficient and widespread in the early universe than previously thought, it changes the origin story of every galactic center in the observable cosmos. The black hole at the heart of the Milky Way might trace its ancestry back to a little red dot that glowed in the darkness 900 million years after the Big Bang. The connection between those tiny red specks in Webb's images and the invisible gravitational giant shaping stellar orbits 26,000 light-years from Earth is not poetic speculation. It is a plausible chain of physical evolution that the new data supports. The overmassive black hole problem carries even more radical implications. In the local universe, black holes and their host galaxies obey a tight scaling relation. The mass of the black hole correlates with the mass and velocity dispersion of the galaxy's central bulge. This correlation is so tight and so consistent across different galaxy types that it strongly suggests a causal connection. Black holes and galaxies must grow together, regulating each other through feedback. When the black hole accretes too aggressively, the energy it releases heats the surrounding gas and suppresses star formation, slowing the galaxy's growth. When star formation proceeds vigorously, it funnels gas toward the center, feeding the black hole. This co-evolutionary dance was thought to be a fundamental feature of galaxy formation. But the little red dots suggest that the dance may not have started in step. If black holes in the early universe were overmassive relative to their host galaxies, as the data indicates, then black holes may have formed first. The engine preceded the city. The black hole assembled its mass rapidly in the dense gas cocoon phase, the little red dot phase, and only later did a galaxy gradually accumulate around it. This would invert the conventional picture of galaxy formation. Instead of galaxies building black holes may have seeded galaxies. This inversion has been proposed before on theoretical grounds, but the little red dots provide the first substantial observational evidence for it at high redshift. If confirmed by continued observations, it would represent a fundamental shift in how we understand the assembly of cosmic structure. The textbooks would not just need updating. The causal narrative at the heart of galaxy formation theory would need to be rewritten. The epoch of reionization adds another dimension to the story, and it is a dimension that connects the little red dots to one of the most dramatic transitions in cosmic history. To understand why, you need to picture what the universe looked like before reionization occurred. After the cosmic microwave background was released, 380,000 years after the Big Bang, the universe was filled with neutral hydrogen gas. This gas was transparent to long-wavelength light, but opaque to ultraviolet radiation. Ultraviolet photons could not travel far before being absorbed by a neutral hydrogen atom. The universe was like a dense fog that blocked all short-wavelength light. This fog persisted for hundreds of millions of years, throughout the cosmic dark ages and into the early stages of cosmic dawn. Even as the first stars began to ignite and the first proto-galaxies began to glow, the surrounding intergalactic medium remained largely neutral and opaque. Reionization is the process by which this neutral hydrogen was gradually stripped of its electrons by ultraviolet radiation from the first luminous sources. As islands of ionized gas formed around early galaxies and expanded outward, the fog began to clear. These ionized bubbles grew and merged over hundreds of millions of years until eventually the entire intergalactic medium was ionized and transparent. By roughly 1 billion years after the Big Bang, reionization was largely complete. The universe had transitioned from opaque to transparent, from dark to luminous, from a cosmic fog to the clear intergalactic medium we observe today. This transition is one of the most important events in cosmic history. It determined when light could travel freely across the universe. It shaped the thermal and chemical state of the intergalactic medium. It influenced the formation and evolution of every subsequent generation of galaxies. Understanding what drove reionization, what sources produced the ultraviolet photons that ionize the hydrogen, is one of the central questions of observational cosmology. The standard explanation attributed reionization primarily to ultraviolet radiation from early star-forming galaxies. Young, hot stars produce copious ultraviolet photons capable of ionizing hydrogen. If enough of these photons escaped from their host galaxies into the intergalactic medium, they could gradually ionize the surrounding neutral gas. This explanation works in principle, but the details have always been uncertain. The fraction of ionizing photons that actually escapes from galaxies, called the escape fraction, is poorly constrained and may vary widely from galaxy to galaxy. Some calculations suggested that early galaxies alone might not produce enough escaping ultraviolet photons to complete reionization on the observed timeline, creating a photon budget problem that has lingered in the literature for years. The little red dots introduce a new potential contributor to reionization. If hundreds of thousands of accreting black holes existed during the reionization epoch, they would have produced significant amounts of ionizing radiation. Accretion disks around black holes generate hard ultraviolet and X-ray photons that are extremely efficient at ionizing hydrogen. A single actively accreting black hole can ionize a larger volume of surrounding gas than a comparably luminous star-forming galaxy, because the higher energy photons from accretion penetrate deeper into the neutral medium. Even if these photons were partially absorbed by the dense gas cocoons surrounding the black holes, some fraction would have escaped into the intergalactic medium. The contribution of accreting black holes to reionization was previously thought to be minor, because the number of active black holes at high redshift was believed to be small. The little red dots suggest that number was dramatically underestimated. If accreting black holes contributed significantly to reionization, it changes our understanding of how the cosmic dark ages ended. The transition from darkness to light may not have been driven solely by the gentle glow of young stars in primitive galaxies. It may have been partly driven by the violent radiation from black holes devouring matter in dense cocoons. Cosmic dawn may have been powered not just by stellar nurseries, but by gravitational engines of extraordinary ferocity. The universe did not merely wake up, parts of it may have been set on fire. But perhaps the most important aspect of the little red dot story is what remains uncertain. Science at the frontier is never clean. The picture emerging from Webb's data is compelling but incomplete. Not every little red dot has been spectroscopically confirmed. Not every spectrum can cleanly distinguish between the competing models. The cocoon interpretation, the direct collapse interpretation, the supermassive star interpretation, and the purely stellar interpretation all have advocates, and none has been definitively ruled out for the entire population. It is entirely possible that the little red dot population is heterogeneous. Some may be genuine accreting black holes, others may be compact starburst galaxies with extreme stellar densities. Still others may be exotic transitional objects like the proposed black hole stars. The Ruby's spectroscopic sensor showed significant diversity within the population, with different objects displaying different spectral features and different degrees of redness and compactness. Treating all little red dots as identical objects and assigning them a single explanation may be an oversimplification. The revised black hole masses from the Watson team's electron scattering analysis, while lower than previous estimates, are themselves subject to uncertainty. The electron scattering model depends on assumptions about the geometry and density structure of the gas cocoon. Different assumptions yield different mass estimates. Future observations with higher spectral resolution and broader wavelength coverage will be needed to refine these numbers and test the electron scattering interpretation against alternative line broadening mechanisms. The direct collapse black hole scenario, while powerfully supported by the Piccucci team's simulations, relies on theoretical models that have not been independently verified through laboratory experiments or alternative computational approaches. The conditions required for direct collapse are extreme and specific. Whether those conditions were actually met in the environments where little red dots formed remains an open question that can only be answered through continued observational characterization of individual objects and their surroundings. The supermassive star interpretation is the most speculative of the three leading models. While the spectral agreement between theoretical supermassive star models and observed little red dot spectra is striking, supermassive stars have never been directly detected or confirmed as a class of objects. Their existence remains a theoretical prediction. Confirming or ruling out this interpretation will require identifying observational signatures that uniquely distinguish supermassive stars from accreting black holes, a challenging task given the limitations of current instrumentation. Follow-up observations are already underway and more are planned. The Ruby's team has additional Webb time allocated to observe the cliff and other extreme little red dots with deeper spectroscopy and broader wavelength coverage. MIRI observations probing the rest frame near infrared will help constrain the contribution of stellar populations versus accretion emission. ALMA observations targeting cold gas and dust will test whether the dense cocoon model is consistent with the millimeter wave properties of these objects. Future X-ray missions with greater sensitivity than Chandra may finally detect the faint X-ray emission predicted by the cocoon and direct collapse models, or place even more stringent upper limits that further constrain the theoretical landscape. The strange disappearance of little red dots after about 1.5 billion years post-Big Bang is itself a major unsolved puzzle, and it deserves careful attention because the answer carries implications as significant as the discovery itself. If the little red dots represent a specific evolutionary phase, what comes after? Where did they go? One possibility is that the dense gas cocoons are eventually cleared by radiation pressure or mechanical outflows from the growing black hole. As the black hole accretes and radiates, the energy it pumps into its surrounding cocoon gradually drives the gas outward. Winds launched from the accretion disk accelerate material away from the center. Over millions of years, the cocoon thins, becomes more transparent, and eventually disperses entirely. Once the cocoon is gone, the black hole would become visible as a more conventional active galactic nucleus, or quasar, no longer red, no longer compact in the same distinctive way, no longer classified as a little red dot. In this scenario, the little red dots evolve into the ordinary quasars and active galaxies observed at lower redshifts. The cocoon phase is a brief, violent chapter in the life of a young black hole, lasting perhaps a few 100 million years before the system matures into something more recognizable. The little red dots would then represent a previously invisible larval stage of supermassive black hole development, a cosmic chrysalis that Webb was the first telescope capable of detecting. Another possibility is that the black holes exhaust their local gas supply and enter a quiescent phase. The dense cocoon that fueled the little red dot phase is finite. Once the black hole has consumed or expelled most of the surrounding gas, accretion slows to a trickle and eventually stops. The black hole goes dark. Without the intense radiation from active accretion, the object no longer glows red or emits the broad spectral lines that defined it as a little red dot. The former little red dot becomes a quiet, massive black hole, sitting at the center of a small, faint galaxy, invisible to most surveys. These dormant black holes might persist for billions of years, gradually accumulating stellar mass around them as their host galaxies grow through mergers and gas accretion. Their presence would be betrayed only by their gravitational influence on surrounding stars, not by any radiation they produce. Eventually, after billions of years of galactic growth, they become the supermassive black holes observed at the centers of massive galaxies in the local universe, the same black holes we detect today through their effects on stellar orbits, and through occasional reactivation when new gas supply reaches the galactic center. The research team, led by Andrés Escala at the Universidad de Chile, explored this question directly in a study examining the likely descendants of little red dots. Their analysis suggested that the most probable evolutionary outcome was for little red dots to become the cause of compact massive galaxies hosting overmassive black holes, serving as seeds for the supermassive black holes observed in the present-day universe. If correct, the little red dots are not just curiosities from the early universe. They are the ancestors of the most powerful objects in the modern cosmos. The quiet black hole at the center of the Milky Way, the dormant giant at the heart of every massive elliptical galaxy, the engine powering every active galactic nucleus in the nearby universe, all of them may have begun their existence as little red dots glowing in the cosmic dawn. A recent and intriguing development has complicated the picture further. In 2025, a team of researchers identified 3 little red dot candidates at much lower redshifts than the main population, meaning they existed much more recently in cosmic history. If confirmed, these local little red dots would be extremely rare, perhaps 100,000 times less common than their high redshift counterparts. But their existence would provide an extraordinary opportunity. Nearby objects can be studied in far greater detail than distant ones. Spectra can be obtained with higher resolution. Spatial structure can be resolved. Multiple wavelength observations can be coordinated across different observatories. If even a few local little red dots can be confirmed and characterized, they could reveal the physical properties of this class of objects with a precision impossible at cosmological distances. They would become Rosetta Stones for interpreting the entire high redshift population. The deeper significance of the little red dots extends beyond any individual object, any single model, or any specific astrophysical mechanism. What makes them genuinely unsettling to the scientific community is the cumulative weight of what they represent when combined with everything else Webb has shown us about the early universe. Before Webb, the first billion years of cosmic history were largely inaccessible to direct observation. Scientists filled that gap with models, simulations, and theoretical predictions extrapolated from later epochs. Those predictions painted a picture of gradual, hierarchical assembly. Small things formed first, big things came later. Complexity emerged slowly. The early universe was a blank canvas being painted one careful brushstroke at a time. Webb has revealed that the canvas was never blank. The first billion years were not a period of quiet preparation. They were a period of extraordinary activity. Stars forming at rates that exceeded expectations. Galaxies assembling masses that challenged predictions. Black holes appearing in numbers and at scales that strained the theoretical framework to its limits. And little red dots, hundreds of them, glowing red from within their dense cocoons, dotting the early cosmos like embers in a fire that nobody knew was burning. The terrifying truth is not that Webb found something impossible. Nothing Webb has observed violates the known laws of physics. Black holes can form through direct collapse. Accretion can proceed at super Eddington rates under certain conditions. Star formation can be more efficient than average models assume. Every individual observation has a physical explanation that fits within the broad framework of modern astrophysics. What is terrifying is the totality. The early universe did all of these things simultaneously, across large volumes of space, in numbers that suggest these were not rare exceptions but common processes. The cosmos was not gradually waking up. It was already running at full power within its first billion years. The machinery of structure formation, the gravitational engines, the stellar factories, the black hole furnaces, all of it was operating sooner, faster, and more aggressively than the comfortable story allowed. This brings us to the question that will define the next decade of cosmological research. Can the standard model absorb these tensions, or will something more fundamental need to change? There are two possible futures for the lambda cold dark matter framework, and both are being actively explored right now. In the first future, the model survives. The tensions Webb has revealed are real, but they turn out to be tensions with our astrophysical assumptions rather than with the cosmological framework itself. Star formation efficiency in the early universe was simply higher than previously modeled. Feedback processes that regulate galaxy growth operated differently in the dense, metal-poor environments of the first billion years. Black hole seeds formed through direct collapse more commonly than theorists expected, but the direct collapse mechanism itself is a natural consequence of well-understood gas physics operating in environments that happen to have been more prevalent than simulations predicted. In this future, the lambda cold dark matter model keeps its core architecture intact. The expansion history of the universe, the nature of dark matter and dark energy, the initial conditions from inflation, all of these remain unchanged. What gets revised is the astrophysics painted on top of the cosmological canvas. The parameters shift, the efficiencies change, the timelines compress. But the foundation holds. This is the outcome most cosmologists currently consider most likely. The standard model is too successful at too many other things to be casually discarded. It matches the cosmic microwave background with extraordinary precision. It predicts the large-scale distribution of galaxies. It accounts for the observed abundances of light elements produced in the first minutes after the Big Bang. These are independent, robust tests that the little red dots do not directly challenge. The early universe producing black holes and galaxies faster than expected does not necessarily mean the underlying cosmology is wrong. It might mean we underestimated what the correct cosmology could produce. But there is a second future, and it is the one that makes theorists nervous. In this future, the tensions do not resolve through astrophysical adjustments alone. The revisions needed to accommodate Webb's findings, higher star formation efficiency, heavier black hole seeds, more efficient accretion, faster assembly of massive structures, accumulate to the point where they collectively strain the cosmological model itself. If the early universe was significantly more productive than lambda-cold dark matter naturally predicts, perhaps the problem is not with the astrophysics, but with the dark matter. Perhaps cold dark matter is not quite cold enough, or not quite collisionless enough, or not quite the right density. Perhaps the initial conditions from inflation had more power on small scales than the standard parameterization assumes, seeding more rapid early structure formation. Perhaps dark energy was not constant in the early universe, but varied in ways that affected the timeline of cosmic assembly. Each of these possibilities represents a deeper challenge to the standard framework than merely revising star formation recipes. If any of them turns out to be necessary, it would signal that Webb has found not just unexpected astrophysics, but unexpected cosmology. The distinction matters enormously. Adjusting astrophysics is like repainting a room. Adjusting cosmology is like discovering the foundation has cracks. The next 5 years of Webb observations will be decisive. More little red dots will be discovered. More spectra will be obtained. The competing models will be tested against increasingly precise data. The Watson cocoon model, the Piccucci direct collapse model, and the Nandel supermassive star model will each make specific predictions that can be confirmed or falsified with targeted observations. If one model clearly wins, it will clarify what the little red dots are and tighten the constraints on what the early universe was doing. If no model clearly wins, and the population turns out to be genuinely heterogeneous, that itself will be informative, suggesting that the early universe was even more complex and varied than any single theoretical framework has yet captured. Beyond Webb, the next generation of observatories will bring additional tools to bear. The Nancy Grace Roman Space Telescope, expected to launch in the coming years, will survey vastly wider areas of sky than Webb, potentially discovering thousands more little red dots and mapping their distribution across cosmic time with statistical power that current surveys cannot match. Ground-based extremely large telescopes with mirrors exceeding 30 meters in diameter will resolve the spatial structure of the nearest little red dots, testing whether they are truly point-like or show extended emission from surrounding host galaxies. Future X-ray observatories with sensitivity far exceeding Chandra will either detect the absorbed X-ray emission predicted by the cocoon model or place limits so stringent that the model requires modification. The little red dots have already changed the conversation. Before Webb, the early universe was a place where simple models could comfortably operate. After Webb, it is a place where models must justify themselves against a growing body of evidence that the cosmos was more extreme, more productive, and more surprising than any framework predicted. The little red dots sit at the center of this shift, not because they are the strangest objects Webb has found, but because they are the most numerous. They are not a single spectacular anomaly that can be explained away. They are a population, they are a pattern, and patterns demand explanations that go beyond exceptional luck. This is the fear that the title refers to. Not a fear of the unknown, a fear of the known. A fear that the data is showing us a universe that became complex and extreme far too quickly for the models that were supposed to describe it. A fear that the opening chapter of cosmic history, the chapter we thought we understood, needs to be rewritten from its foundations. The little red dots are not the end of this story. They are the beginning of a new one. Webb continues to observe. New spectra are being collected. New models are being tested. The debate over what these objects truly are is far from settled, but whatever the final answer turns out to be, one thing is already clear. The early universe was not the quiet, simple, slowly maturing place that scientists spent decades expecting. It was a furnace. It was building monsters, and it started far sooner than anyone was prepared to believe. Webb did not find what scientists hoped. It found what they feared. Evidence that the cosmos refused to wait. Evidence that the darkness after the Big Bang was not empty at all, but seething with creation and destruction on a scale that the universe would never again repeat. The little red dots are the proof, and they are still glowing 13 billion years later in the infrared eyes of a telescope that was built to find them. even though nobody knew they were there.